Hello and welcome to the fourth lesson in Area of Study 2. Today we're going to be taking a look at the application of lessons 1 to 3. And in lesson 4, what we're doing today is transmission lines. So what are we going to do? We are going to do a quick review of transformers before introducing the main topic, which is transmission lines. We're going to look at why power is stepped up or voltage is stepped up and down, and then we'll be having a look at power loss and voltage drop. We'll then wrap up with a comparison of AC and DC power. So, as a review of transformers, hopefully you remember this. We have an input and an output, primary and secondary coils respectively. And in a step-down transformer, there are more coils or more turns in the primary coil. In a step-up, there are more turns in the secondary. And the turns ratio represents it's quite literally the ratio of the turns between the primary and the secondary coil. We also had these formulas here that gave us a relationship between the turns ratio, the voltage, and the current in each of the coils, and we also noted that power is the same across both the primary and secondary coil. And at the bottom there is a bit of a summary on what happens to current and voltage in a step up and step down transformer. So on to the main topic of today. Transmission lines are an interesting topic. They come up pretty much every exam, and it's a very good application of what you've learned in terms of its practicality. So if you were to design a transmission of electricity infrastructure system, you would be taking into account the exact same things that we're going to be taking into account today. And what that means is we are going to figure out what we can generate. So on the left there, I've got some generators. We're going to figure out how we can transform the electricity into something that makes it as efficient as possible. And we're going to calculate how much of that energy, or the efficiency of the system, how much of the energy that we deliver to the system we're going to get out at the end. And we'll be transforming the voltage at the end of this transmission down to a voltage and current that is actually useful. Obviously, real life is a little bit more complicated. There are things like substations and the like. And obviously, there are series and parallel circuits that we're not going to explore in great detail. However, that being said, the concepts that you will have learnt from those first 3 lessons are going to be very important when we come to this. So what is power loss and voltage drop? So those two are separate concepts, but they're quite closely related. Power loss is essentially the amount of energy that we lose through the transmission. And a lot of students get confused with the amount of power you supply and you get delivered with the power loss. Now there's a formula, very straightforward formula. The power that you put it in is equal to the power you get out plus the power that's lost. That's not on the slide here. It's just a bit of, I guess, common sense in some ways. Voltage drop, on the other hand, is essentially how much of the potential difference we've lost due to resistance in the line. And that is a separate formula down the bottom there. So the voltage drop is the current through the line multiplied by the resistance in the line. Now, you'll notice that if you were to get rid of the subscripts there, so V equals to IR, that's a formula that you're probably quite familiar with, and the same with power. So P is I squared R. The important thing to note is that in our case, we're considering only thing within the power lines, the transmission lines. And that changes our result. So we'd only be looking at power loss and voltage drop when we consider those values. That's a really, really important thing to note, and you should probably be writing that down somewhere so that you remember it. Just reading through this slide, you can see that what I have put there in that diagram isn't the full diagram. So it's a simplified version. We go back, you'll see that I had the generator, then the first transformer, then the transmission lines, then the second transformer. Similar idea here, except for a couple of differences. Obviously, the main difference is that I haven't drawn in the generator, which would be over here somewhere. And I also haven't drawn the output. That might be a home or something. The transmission lines are essentially little bits of resistors, which are those things over there. So in this case, I know we've got two transmission lines, so there are resistors in each line. Other than that, there isn't much more to add for power loss and voltage drop. It's simply a calculation. And the thing that you should note is that it comes as a result of having resistance in a line. So the really big question, not just within this, but how do we move things efficiently in general, is a problem that has been on the mind of physicists and, funnily enough, economists in different senses, to try and build an efficient system. So what we want to do in our case with transmission lines is minimize that power loss. Now, if we go back to the equation of power loss, it's I squared R. And so that means that the dominant term, so something that's going to have the most impact, is going to be our current over here. If we can somehow minimize our current, we're going to end up with a lot lower power loss. So that kind of brings us to that third dot point, that minimizing current will optimize our efficiency. Now, ideally, you're going to have current at 0. But if you were to think about it, current at 0 would literally mean that you're not delivering any electricity. So we don't really want that. It's also potentially prohibitively expensive to keep stepping up voltage and therefore lower current. So that's another consideration. We don't want to be doing too much, otherwise it's just not very useful. Finally, we've got to consider the safety. So if we step up voltage really high, there are impacts. So you'll remember from the right-hand grip rule, if you have a current, you're going to have a magnetic field, and if you keep stepping up that voltage, then that's going to impact something there, and you're going to end up with additional forces on your transmission lines. There's that as a safety characteristic, but also what happens in, for instance, a lightning strike. You don't want to completely destroy the entire thing and set, I don't know, places alight. So those are the things that we kind of have to take into consideration. And the result is we use a transformer to manipulate current to a relatively low level, not 0, and not necessarily 0.00 something, but something reasonable that isn't going to be prohibitively expensive, that's going to allow the voltage to be relatively safe. So when we carry out whatever maintenance we wanted on it, that would be fine. That's the theory behind moving electricity efficiently. It's minimizing power loss by minimizing current, but not necessarily putting current to a really tiny value. Let's take a look at the first practice question. So a power station generates a total of 5 times 10 to the power of 4 watts at a voltage of 500 volts. A transformer steps up the voltage, so it becomes 25,000 volts at the start of the transmission lines before stepping it back down in the same ratio. For 2 marks, I'd like you to draw a diagram of this scenario, and it doesn't have to be super artistic. I know that when I answered these types of questions, it was quite rudimentary, but they do come up relatively frequently. So it's always a good idea to have a bit of practice with it. So 2 marks. If you spend lots of time annotating your diagram, it may take you longer than 2 minutes, but keep it reasonable. All right, now that you've had a go at that question, we can take a look at what I have prepared. Now, I've got a slight advantage in that I can reuse diagrams, so that's exactly what I've done. I have put in my generator. I've specified what the output from that generator is. It's 5 times 10 to the 4 watts at 500 volts. That's fine. It's just a label diagram. It doesn't have to be in words particularly. We've got the first transformer there. I could have put in the turns ratio. Again, you don't have to, probably should. So I would write something along the lines of 1 to 50, because it steps it up by 50 times. And you can see that when you do 50 times 500 is 25,000. So this is 1 to 50. And you could obviously do the same over here, 50 to 1. And that would be completely reasonable. I've put a direction, so off to the right is towards the customer. You don't really have to do that. You could just draw a little house or something like that, just to show that you understand the flow of electricity through this diagram. State the turns ratio in the first transformer. 1 mark, and as a slight hint, I've already said the answer, maybe by accident, maybe not. All right, now that you've hopefully done that question in less than 20 seconds, it's 1 to 50 because we have our input as 500 volts, our output at 25,000 volts, which is 1 over 50, so that's the ratio, 1 to 50. Now, if you said 50 to 1, you might be thinking of the second transformer, or perhaps you've mucked up your equation, the order in which you've done things. Part C is find the current in the secondary coil of the first transformer. It's worth 2 marks. Probably should add an S there. Yeah, it's 2 marks, not just 2 mark. Anyway, and yeah, 2 minutes to do this question. All right. Now that you've hopefully had a decent attempt at this question, we can run through the solution. So what do we have? I'm going to whip out the classic equation that we need to use. So we've got the input voltage over the output voltage is equal to the output current over the input current. That follows straight from the turns ratio. You substitute that in, and we can find our input current. So using our power over voltage, we get 100. And so we multiply that by 1 over 50 and we get 2 amps. So the answer is 2 amps of current in the secondary coil of the first transformer. Mark allocation for 2 marks, you'd get 1 mark for, I guess, stating and using the turns ratio. So it's kind of those first 2 lines there, and you get your other mark for the answer. All right, calculate the power loss through the transmission lines if the resistance in each of the wires, each of the 2 wires is 10 ohms. It's worth 2 marks. You may wish to draw a diagram or use your diagram with your answer, just so that you, and obviously your answers to previous questions, so that you know what you need to do. All right, now that you have hopefully had a decent attempt at that question, we can go through the answer. So we need to use this equation. Power loss is the current in the line squared multiplied by the resistance in the line. Now I know I haven't put the subscript of line in each of them, because I'm assuming that you know that because it was in an earlier slide. We then put in our values, and you may be wondering, why is it 10 plus 10? Well, because it's the resistance in each of the 2 wires. So we've got to add those wires up. So the total resistance is 20 ohms, and therefore we get a power loss of 80 watts. That's how you go through that. 2 marks, you'd get 1 for the second step, so putting in the 10 plus 10 bit mostly, and then another mark for your answer. If you did get previous questions wrong, Consequential marking is pretty easy to apply, so don't really worry about that too much. All right, next one, calculate the voltage delivered to the secondary coil of transformer 2, or the second transformer. It's worth 3 marks, so you're going to have to do a little bit of work to get there. Again, use your answers from previous questions to help you out. All right, now that you've had an attempt at that question, we can go through the answer. So the first thing to do is to figure out how much voltage is dropped over the transmission lines, and that's using that formula there. Pretty easy to do. You again use your resistance from the previous question, 20 ohms multiplied by the current, you get 40 volts. Now we know that the voltage at the primary coil of the second transformer is given by whatever came into that transmission line less dropped. So we're going to end up with 24,960 volts at the primary coil of transformer 2, and we have to then divide it by 50 because we use the turns ratio but in reverse to find that our output is 499.2 volts. Now you could have given that as 499 volts, that's fine. There is a bit of a debate amongst teachers and students as to how many decimal places / significant figures you give things in electricity to. It's currently, as I understand, still up for debate, but the answer is that VCE don't really care too much as long as the answer is correct. So that's just something that you may wish to look at when you do practice exams. You may also notice that there are quite a lot of decimal places or significant figures given in the answers that they provide. So that's a little bit about that potential issue. So now that we have that question under wraps, mark allocation, you get 1 mark for your final answer. You get another mark for finding the voltage drop and finding the voltage into the first transformer. So that's pretty much how that works. Not too complicated, hopefully. Part 1F, find the efficiency of this system in percentage terms correct to decimal places. Worth 2 marks, although you could potentially argue that it'll only be a 1 mark question. I've been generous and decided to give you 2 marks for this question. Righto, hopefully you've had a good attempt at this one. The way to calculate efficiency is with voltage over, or voltage out over voltage in, usually the best way of doing it. You could also do power out divided by power in, you get the same result. And here we have 499 onto 0.2 over 500, and you get an efficiency of 99.84%. Now, bit of a disclaimer, you're never really going to find something that is that efficient in real life. That's insanely good, but this is all, I guess, made up numbers, really, how I've done this. So you're more likely to get 98, 99% if you were to have actual figures. Perhaps if you were to do a prac, you can, I guess, make your own small transmission line circuit and calculate the efficiency of it. You probably find that you get a decent result. Might not be quite this high, but it'll still be relatively high because there are lots of factors that are in actual transmission lines that aren't in the ones that you do in a prac. So that obviously impacts the results that you get, but this is a fairly efficient system. Now, this is an interesting question because I haven't really gone to a lot of depth on why AC power is used rather than DC power for the transmission of electricity, but hopefully you've done a bit of study in class or otherwise. If not, don't necessarily worry, you can just look at the solution. I'll give you some time to have a go at it. All right, now that you've hopefully potentially had a go at this question, we can run through the answer. So there's a few points here. The first is that AC power has, there are actually quite a few advantages. The first is that you can step up voltage to reduce transmission losses and therefore step down current. Another advantage is the ability to step down voltage and match the consumer's requirements, wherever they may be. So home business, DC power can't be stepped up or stepped down because it's a direct current. And by Lenz's law, it's not going to induce a current in the secondary coil. Finally, AC is safer than DC, and that mainly comes from the idea that and if you get shocked by it, you're not having a constant penetration of current, you're having an alternating current. So it reduces injury and harm, and those are the 3 points, the main 3 points that you could argue when you're talking about the benefits of AC power over DC power. Specifically with the transmission of electricity. There are other advantages outside of that, but this question asks for that, which is relevant to the transmission of electricity. So you get a mark for each point, really. Nothing too complicated there. And that brings to an end the contents for this lesson. As a quick review, we had a look again at transformers for literally a couple of minutes at the start before we moved on to the fundamentals with transmission lines, formulas related to that. That includes power loss, voltage drop, etc. We had a look at stepping up and down current and voltage. And then in the last question, we looked at a comparison of AC and DC power. Thank you very much for your attention. Hopefully you found this lesson to be at least semi-interesting and that you learned something new. If you want to get in touch, you can head to airlearners.com and find me on the tutors page. In our next lesson, we're going to be taking a look at the generation of AC powers. That's going to look at generators, which kind of leads on from this when we're talking about generating electricity. So look forward to that. Otherwise, that's all from me. I'll see you next time.